In the previous two sections, we have discussed how to compute double integrals over both rectangular and non-rectangular regions. We still want to maintain our concentration on double integrals, but in this section, we're going to focus on how we can utilize polar coordinates to simplify our computation for various double integrals. So first, let's define what we mean by a simple polar region. A simple polar region in a polar coordinate system is a region that is enclosed between two rays, theta equals alpha and theta equals beta, and two continuous polar curves, which will denote r sub 1 of theta and r sub 2 of theta, where the equations of the rays and the polar curves satisfy the following conditions. Number one, we need that alpha is less than or equal to beta. So one is always bounding above the other. Two, that beta minus alpha is less than or equal to 2 pi. So we're not going to allow them to be more than 2 pi apart. And then finally, that R1 of theta is greater than or it's less than or equal to R2 of theta. So those polar curves aren't crisscrossing back and forth. Let's sketch a little diagram of what a polar region might look like. I'm going to sketch vertical and horizontal axes. And then I'll draw my two rays, theta equals alpha and theta equals beta. The lower one is alpha, and the higher one is beta. And then sketch two polar lines. I'll draw one kind of wavy. This is r equals r1 of theta. And I'll draw the other one to look kind of like an arc of a circle. This is r equals r2 of theta. And now what we have is this region that's bounded by the four lines and curves is going to be our simple polar region. Now you can see here that if we wanted to use rectangular coordinates here, it's going to be a bit of a nightmare because depending on where you draw your arc, your bounding curves and lines are going to change. And so we'll see how polar coordinates are going to greatly simplify our computation for an integral whose domain is over this region. All right, so next to definition, given a function f of r theta that is continuous and non-negative on a simple polar region, the volume of the solid enclosed between the region r on the xy plane and the surface whose equation in cylindrical coordinates is z equals f of r theta is given by this volume integral. Very similar to what we saw in 14.1, just stating that the volume beneath the surface f over the region r is the double integral of f over r. The integral above is the polar double integral of f of r over r. All right, so what we want to do is we want to jump into an example that will utilize using polar coordinates in a double integral. This first one here is just going to be set up for us. So we evaluate polar double integrals the same way as rectangular double integrals. And let's go ahead and evaluate this iterated integral. All right, so first we want to integrate with respect to r. I will rewrite my first integral, and then I will integrate with respect to r. So I have a 1/2 r squared, and I want to evaluate r from 0 to cosine of 3 theta d theta. All right, and so of course, when I plug in 0, that drops out. So I'll just plug in cosine of 3 theta. All right, now at this point, we recognize that we're integrating a cosine squared. So we need to remember our half angle formula from trig. So we have that cosine squared of theta is 1/2 of 1 plus cosine 2 theta. Now, in our instance, instead of having a theta, we have a 3 theta. So keep in mind that when you apply this formula, you double the inside of your cosine. So our 3 theta is going to become a 6 theta. So I have my 1/2, and then applying that half angle formula, I get my second 1/2 right here, and then a 1 plus cosine of 6 theta. And this is d theta. All right, so in other words, I have a 1/4 integral from 0 to pi 6 of 1 plus cosine 6 theta. Now, if you want to show your u substitution here with your 6 theta, that's perfectly fine. I'm just going to kind of do it in my head and recognize that it's going to pop out a 1/6. So I have 1/4 theta plus 1/6 sine of 6 theta, all of this from 0 to pi 6. Now, since sine of 0 is 0, I know that when I evaluate this expression at 0, the whole thing is going to zero out. So I'll just plug in pi 6. And we see that that sine function becomes the sine of pi, which goes to 0. And so in the end here, I have an answer of pi over 24. All right, so continuing on, we have theorem 3 that says if R is a simple polar region whose boundaries are the rays alpha and beta, and the curves R1 and R2, and if f of R theta is continuous, then we can take our double integral and we can rewrite it with the following limits of integration. We have our theta limits from alpha to beta. We have our R limits from R1 of theta to R2 of theta. And what I really want to call your attention to is that our differential dA becomes R dr d theta. So if you think back to 14.1 and 14.2, our dA became either dx dy or dy dx, depending on what type of region we were working with. Here, our dA in a polar region becomes r dr d theta. Now, I'm just going to have you take my word for it, and we'll see in a later section where that factor of r comes from. But for now, let's just roll with it. And I want to remind you of the relationships between polar and rectangular coordinates. We have x is r cosine theta, y is r sine theta, and then the Pythagorean theorem tells us that r is the square root of x squared plus y squared. And finally, theta is related to x and y by the formula tangent theta is y over x. We will use these four when we're transforming a function f of x, y into a function f of r theta. So just kind of keep those in the back of your mind while we're working out these problems. So for the remaining examples, we're going to want to switch a double integral from rectangular to polar coordinates. So use polar coordinates to evaluate the double integral. Here we're giving our region in words. R is the region in the first quadrant within the circle x squared plus y squared equals 9. So I'm just going to go ahead and sketch that region. It's not too complicated. We have a quarter circle in the first quadrant. We have radius 3. All right. And so first, let me rewrite the equation of the circle into polar coordinates. That can be rewritten as r equals 3. I can also express those boundary rays. In this case, they look like the x and y axes in polar coordinates. The x-axis is theta equals 0. The y-axis is theta equals pi halves. And in this case, it's hard to see an inner boundary polar curve. You'll notice that we want to go all the way out to r equals 3, but this inside, we almost don't even think of it this way, is r equals 0. So here is our polar region. And now let's go ahead and set up our double integral. I'll come back to those limits of integration, but first what I see is the square root of 9 minus, if you factor out a negative, that's an x squared plus y squared. So I'm going to use the fact that r is the square root of x squared plus y squared, and I can replace that with an r squared. And then again, our dA becomes r dr d theta. And so what are our r limits of integration? We're ranging from r equals 0 up to r equals 3. And our theta limits of integration are from 0 to pi over 2. So now we have our setup. Now we just need to go ahead and carry out the integration. What's nice about this extra factor of r is it's saving us from doing trig substitution. Instead, we can do a u substitution. U is 9 minus r squared. Du is going to be a negative 2r dr. And so r dr is a negative 1/2 du. And we see r dr right here. So we're going to substitute that in. You can also decide if you want to change your limits of integration or if you want to resubstitute back in terms of r. I'm going to go ahead and change my limits of integration. So if r equals 0, then u is 9 minus 0 squared, which is 9. And if r equals 3, then u is 9 minus 3 squared, which is 0. All right, so we actually see our limits of integration changing here from 0 to 3 to 9 to 0. The outer limits of integration we're going to leave. And then we have the square root of u times a negative 1/2 du d theta. Okay, so thinking of that u as a u to the 1/2, when I integrate, I'll add 1 to the exponent, becomes 3/2, and multiply by its reciprocal 2/3. So I'll leave my negative 1/2 out front. This is a 2/3 u to the 3/2. And then I want to evaluate u from 9 to 0 d theta. And of course, I can cancel out my 2's on top and bottom. So here's my negative 1/3. When I evaluate at 0, I get 0. And then u to the 3/2 is the square root cubed. So I'm going to plug in 9 in that way. Oops, that's not a du, that's a d theta. And so the square root of 9 is 3. 3 cubed is 27. I have a double negative, which makes it positive. 27 over 3 is 9. So there's a lot of arithmetic there, but when the dust settles, this becomes just a 9 d theta. And then of course I can carry out this last iteration of an integral. So I get a 9 theta from 0 to pi halves, which gives me a 9 pi halves. So again, the interpretation is the volume beneath the surface defined by the square root of 9 minus x squared minus y squared over that quarter circle that we drew in the xy plane is 9 pi halves cubic units. I have one remark here at the bottom of page 2. It says we may also convert double integrals in rectangular coordinates to polar coordinates, meaning if we're given an entire double integral in rectangular coordinates, including the limits of integration, we can then transform that to a double integral in polar coordinates. All right, very important here, to determine the proper limits of integration for polar double integrals, it's helpful to draw the region. All right. So our next two examples are going to illustrate working on this skill. All right. Evaluate the iterated integral by converting to polar coordinates. So first, let's just take a look at this integral. What we see is a complicated integrand in that we have that x squared plus y squared, which is just screaming to be transformed to an r squared. And we also have rather complicated limits of integration. And so once you get used to working with these regions, you'll be able to recognize that these limits of integration are working with a circle. And let's see why that is. All right, so what I have here is my y limits ranging from 0 to 1, and my x limits are ranging from 0 to the square root of 1 minus y squared. Now let's zero in on that upper limit on x. And for just a moment, I'm going to write equality. If I squared both sides, I would get x squared equals 1 minus y squared. And then moving the y squared over, I get x squared plus y squared equals 1. So we see this to be related to the unit circle. However, one thing that's very important is notice that in the way that it's written up here, I only want the semicircle where x is positive. So even though this equation of the full unit circle is algebraically equivalent to this equation up here, notice that when I introduce that square root, square roots can only output positive numbers. So in this equation right here, we know that x is greater than or equal to 0. So when I sketch this region, I'm only going to include the semicircle for positive x values. So it's going to look like this. Okay, and so here's what we get for our region when I look at my x limits of integration. But now what I want to do is I want to look at my y limits of integration. Y is only allowed to range from 0 to 1. So I'm going to x out this lower quarter circle because that has y values that are negative, and I'm only going to shade the part of the semicircle that has positive y values. All right, so now what I've done is I've drawn my region using the rectangular limits of integration. And now let me write out my polar equations that are bounding this quarter circle. So I have the unit circle r equals 1. On the inside, I go all the way to r equals 0. So I'm allowing all of the quarter circles whose radii are between 0 and 1. Then, of course, the x-axis here is theta equals 0. The y-axis is theta equals pi halves. So you can see that radially, we're allowing radial lines from 0, pi 6, pi quarters, pi thirds, all the way up to pi halves to get that entire region. All right, I think the hard work here is done. We can go ahead and set up our double integral in polar coordinates. So our integrand is going to become a cosine of r squared. Remember, our dx dy is dA, and in polar coordinates that transforms to an r dr d theta. I want to emphasize here that the order of integration is already determined for you. It's always going to be dr then d theta. So our r limits of integration are from 0 to 1. Our radius of our quarter circle is 0 to 1. And then our theta limits are 0 to pi halves. And by the way, so far we've only seen r limits of integration from 0 outward. Had our quarter circle looked like this, like a piece of a rainbow, We might have had from r equals 1/2 out to r equals 1, and we would lose this kind of inside piece, right? So you really just have to look at your region to identify, is r running from 0 to 1, or is it running from some other value? All right, so now we're going to carry on similar to our last example with the u substitution. U is r squared. So du is 2r dr, or r dr is 1/2 of du. And again, what I'm going to do is I'm going to change my limits of integration. When r is 0, u is 0. And when r is 1, u is also 1. So it just so happens that our u limits of integration are going to be the same as our r limits of integration. So I have the integral from 0 to pi halves, the integral from 0 to 1 of a 1/2 cosine u du d theta. All right, so the integral of cosine is sine. And I want to evaluate that from u equals 0 up to 1. And I know that sine of 0 is 0. I don't know what sine of 1 is, so I'm just going to leave it as sine of 1, but that's some number. And so this entire integrand, 1/2 sine of 1, is a constant. When I integrate it with respect to theta, I'm just going to tack a theta on there. And then, of course, when I evaluate, I'm just going to get a pi halves popping out. So this becomes a, excuse me, not pi halves, but pi quarters sine of 1. All right, and there is my answer for that double integral. We have one more example here, 34, very similar. All right, first thing I want to do is I want to note that in my integrand, I have an x. I'm going to transform that using the equation x equals r cosine theta. All right, now let's take a look at our limits of integration. I see that y is ranging from a positive square root of 16 minus x squared to a negative square root of 16 minus x squared. Now, again, if I do my same trick where I just look at equality for a moment, if I square both sides and shift things around, what I get is x squared plus y squared equals 16. Now, in the last example, I was really careful because I was only looking for the positive square root. In this example, I'm actually looking for the positive and the negative square root. So I'm going to get negative y values and positive y values. So I'm going to sketch the entire circle of radius 4. So I'll indicate my radius here. And I'll also note that that equation transforms to r squared equals 16. But remember, we're assuming here that r is always positive. So we'll write it as r equals 4. All right, now let's take a look at our x limits of integration. X is bounded between -4 and 0. So I don't want any positive x values here. I only want the pieces in the circle where x is between 0 and -4. So that's just the left half circle here that I have shaded. And let's go ahead and mark those radial lines. I want to sweep from pi halves all the way down to 3 pi halves. All right, so those are all of the radial lines that I want to sweep out that region. All right, I think I have everything that I need to get started. I'm going to actually set up my integral over here in the margin so that I make sure I have enough room. We discussed that that inside is going to be a 3r cosine theta. Then my dy dx becomes an r dr d theta. My r limits of integration are from 0 to 4, and my theta limits of integration are from pi over 2 to 3 pi over 2. Now let me go ahead and combine these two r's to give me an r squared. Recopying my integrals and writing this as 3r squared cosine theta dr d theta. All right, so I'll rewrite my outer integral, and this is going to become an r cubed cosine theta, where r is ranging from 0 to 4 d theta. Of course, when I plug in 0, I get 0 back out. So I'll just evaluate at 4. 4 cubed is 4, 16, and 64. So I have a 64 cosine theta d theta. The integral of cosine is sine. So I get a 64 sine theta, where theta is ranging from pi halves to 3 pi halves. So that's 64 times sine of 3 pi halves minus sine of pi halves, which is 64. Sine at 3 pi halves, so let me grab a different color here. We're looking down here, and now this is a circle of radius 4, but if it were radius 1, we would be at 0, -1. Remember, sine is the y coordinate. So I have a -1 here at 3 pi halves, and then take away at pi halves, the y value is 1. So I have 64 times -2. So my final answer here is -128. All right, this concludes section 14.3, double integrals and polar coordinates. Up next in 14.4 is going to be surface area and working with parametric surfaces.